Hey everyone! Today we're going to talk about volumes of prisms and cylinders. So we're going to talk about how we can find the volume of a prism or a cylinder, and maybe it's not a right prism or a right cylinder. And a right cylinder is like a can of vegetables. We're going to talk about things that maybe tilt, lean sideways. And we're also going to talk about classifying solids. We're going to learn some new vocabulary, and then, of course, finding some volumes. So, our first vocabulary word is polyhedron, which is a solid, a three-dimensional figure bounded by polygons, which means that there are no curved edges. So, I can write that. Only straight lines. Everything is connected, but each face, each side of your polyhedron is of polygons, no curves. And a face is just a flat surface of a polyhedron. Any flat side is a face. An edge is a line segment formed by the intersection of two faces. So an edge is the connection point between two faces. A vertex is just like a vertex of a 2D figure. It's the corner where edges meet. And volume is the number of cubic units contained interior of a solid. So it's how many cubes can fill a space up. And we know that volume can also be measured by liquid. This concept is brand new today. It's called Cavalieri's principle. Cavalieri was this Italian mathematician in the 1600s. And this is one of his big things that he found is that if two solids have the same height and cross-sectional area at every level, they have the same volume. Essentially, this means as long as your figure, all you're doing is tilting it, the volume stays the same. And this can be explained well through coins. So if you can see this image here, stack of coins, and then I'll show you this picture where they're slanted, tilted sideways. Even though it's slanted a little bit, the volume is the same. There's still the same amount of quarters in each stack. Or, the example like the Leaning Tower of Pisa. This tower, has the same volume as it did originally, even though it's leaning now. So, things that are tilted, we can find the volume of them the same way we do as something that's standing upright. And then we've got this concept of similar solids, which are two solids of the same type, so like a cylinder and a cylinder, prism and a prism, with equal ratios of corresponding linear measures, which means that, if you have a radius of this smaller one and a radius of this larger one, you can multiply by some scale factor k to get to the larger value. That is a times k, multiply by k. And there's an interesting property of the volumes of solids, the volumes of similar solids that we'll talk about today. So let's flip the page and talk about these different words we can use to describe solids. So here we have this word polyhedra again, and this is like a T chart, so you could even draw this if you wanted to. So remember, polyhedra, the faces are all polygons, and we have these things called prisms and these things called pyramids. Prisms are where both bases, the bases are like this side that we can't really see and this side here, they're both polygons. Like these are both rectangles. And a pyramid has one base, and then the other base is not a base, it meets at a point. And then we have different options for non-polyhedra, which we have our cylinder, like a can, a cone, and a sphere. We're going to talk about all of these figures later on. Okay, Here's our first example, classifying solids. Tell whether each solid is a polyhedron. If it is, name it. All right, this first one. Is this a polyhedron? Are all of the faces polygons? Yes, they are. So I'm going to write yes, it is a polyhedron, excuse me. And now, what kind of polyhedron is it? Is it a prism or a pyramid? You see there is one base, a 1, 2, 3, 4, 5 pentagon base, and a dot here. So we can actually call this a pentagonal pyramid. Pentagonal, like a pentagon, the base is a pentagon, pyramid. All right, how about this next example? Is this a polyhedron? No, because the base is a circle. This is a semisphere, half a sphere. Polyhedron. All right, not a polyhedron. And this next one, is this a polyhedron? Are all the faces polygons? Yes. It is. All of the faces are either rectangles or hexagons, so it is a polyhedron. And now, is this a prism or a pyramid? It's a prism because it has two bases, two hexagon bases, so we can say this is a hexagonal pyramid. Ooh, I just said the word pyramid, but that's not what I meant. This is a hexagonal prism because there are two bases. Excuse me. All right, that's classification. And now, this is where we get into that Cavalieri's principle. So even if you have a prism that's tilted like this, where the sides are parallelograms instead of rectangles, you can actually find the volume the same way. So the volume of any prism at all, is V equals base times height, where B is the area of the base and H is the height. So you always have to figure out what the base is and find the area of the base, whether it's a triangle, a trapezoid, a square, a rectangle, a pentagon, whatever it is, and where H is the height. Okay, so for this one, our triangle is the base. So we can say volume. Actually, no. I'm gonna find the base first. The volume, oh goodness. The area of the base is the area of this triangle. This is a triangular prism because the two bases are triangles. So how do we find the area of a triangle? 1/2, base times height. Where this H is different than this H up here, it's the height of the triangle. So maybe I'll mark it H little t for height of the triangle. So this base has to be 1/2 base, so 5 times the height, which is 8. Let's see, 1/2 times 5 times 8 is 1/2 of 40, which is 20. So that means the area of the base is 20. And then what's the height of our prism? That's like how far back it goes. That'll be this 3. And now finally, we can write that the volume of our prism is the area of the base times its height, which is 20 times 3, which is 60. And its volume now, and volume is in cubic units, so we'll say 60 cubic centimeters is our final answer. All right, how about this second example? This is another prism, and its base is a trapezoid. Oh, I should actually write that here. I'm going to write that up here. This one was a triangular triangle base. This one's a trapezoid base. So how do we find the area of a trapezoid? Because we got to find the area of the base first. That is 1/2 times its height, the height of the trapezoid, not the height of the prism. So I'll write HT again, like last time. Times the first base of the trapezoid plus the second base of the trapezoid. And this is a formula that you could Google if you've forgotten. So the area of the base, the area of this trapezoid is 1/2 times the height of the trapezoid. Here, I'm just going to mark out this trapezoid. The height will be this 2.5 number. Base 1 will be 5.6. And base 2 is 4.4. Oh, but we're not multiplying those. Excuse me. Let me back up here. We're adding those. That's the formula for the area of a trapezoid. Whew. Well, let me get out my handy dandy calculator. First, I'm going to do what's in the parentheses. We're going to do 5.6 plus 4.4. That's 10. Times 2.5, 25, divided by 2, 12.5. Well, actually, we didn't need a calculator, did we? 12.5 is the area of the base. And now the height of our prism is this back number, so 4.2. All right, and now the volume is 1/2 times the area of the base times the height, which is 1/2 times 12.5 times 4.2, which ends up being, I'm out of room, but it ends up being 52.5. Or does it? No, it doesn't. Where did that 1/2 come from? It's just base times height. Oh my goodness. I'm so sorry, y'all. Not a 1/2. You're probably wondering where that came from. Nowhere. My brain. I don't know. That 1/2 doesn't exist. Excuse me. It's just base times height. Okay. Give me 1 second. We're gonna just fix this real quick. It's just base times height. Oh man. So this is 12.5. I think maybe I was thinking about the area of a triangle again or something. Times 4.2. And this equals 52.5 cubic meters. So I'm just going to kind of write that down here. 52.5 cubic meters. And that's our final volume. Ooh, all right. So the volume of a prism, no matter what kind of prism it is the area of the base times the height. So you have to figure out what the shape the base is and then find the area of that base. Now we're going to talk about volume of cylinders. And it's actually the same formula, y'all. Area of the base times the height. But for a cylinder, the base is always the same. The base is always a circle. So we can maybe simplify this to just being the area of a circle times the height. And that's why this is pi r squared, because this is just the area of a circle. Okay, how about an example? Finding the area. I guess I don't have instructions, but this is find the area. Find the volume, of each cylinder. So the volume of a cylinder is pi radius squared times the height. And in this one, that 5 is the radius and the 9.1 is the height. So our volume is pi times 5 squared times 9.1. Let's see, 5 squared is 25 times 9.1 is 227.5. So that means our volume is 227.5 pi. And this is our exact answer. So if Big Ideas ever asks you to find an exact answer, that means leave it in terms of pi. But we can also approximate this by actually taking 227.5 times pi. And that gets us 714.71 cubic meters is our label. And that's our approximated volume of that cylinder. Now, how about this next example? What's our radius? 7 is the radius. What's the height? 22. So you might notice this height is outside of the cylinder. The height is just the vertical distance from your base 1 to your base 2. Not the actual distance between those two bases, just the vertical distance. So, volume, pi r squared, so pi times 7 squared, times the height, which is 22. Let's see, 7 squared is 49. 49 times 22 is 1,078. Times pi, that's our exact answer, and we can approximate that to be 3,086.64 cubic feet. And we got that by taking 1,078 times pi. That's the volume of a cylinder. All right, and two things left, similar solids. So we talked about this in the beginning, but similar solids have a fun property with areas. So two solids with the same type with equal ratios of corresponding linear measures, this just means they are similar. They're similar. And the ratio of their corresponding linear measures is called the scale factor. It's what you have to multiply one length by to get the other length of your other figure. So if two solids have a scale factor of k, then the ratio of their volumes is equal to k cubed. So we're going to talk about what all this means in this example. So we've got a square prism A and a square prism B, and they are similar. And a square prism is just a cube. So I'm going to draw two cubes. I think that will be helpful. My drawing skills aren't awesome, but we can kind of try to picture this guy. So this is prism A, square prism A. Each base is 4. How about square prism B? It's a little bit bigger. This is prism B. Each base edge is 6 inches. The volume of prism B, oh, it's not a cube, excuse me, it's a square prism, so it might be longer. Anyways, the volume of prism B is 135 cubic inches. The question is, what's the volume of prism A? And there is a shortcut we can use. But I think I want to do it the long way first, just so you can see where that shortcut comes from. And then after this, you can use the shortcut. So what I want to do first is find this height of this, or excuse me. Oh, I drew these incorrectly. Oh, I'm sorry, y'all. This is not 6 and this is not 4. This top part is this line right here is 4 and this line right here is 6. And we don't know their heights. But we can find the height of prism B because the volume equals the area of the base times the height. And we know the volume is 135. We know the area of the base is 6 times 6 times the height. So 6 times 6 is 36. So I'm going to take 135 divided by 36, and that's our height. So that means our height right here is 3.75. Okay, and now I want to use the scale factor to find the height of our prism A and then find the volume of prism A, and then compare them. And you're going to find out something pretty cool. So, what's the scale factor? What do I have to multiply by 6 by to get to 4? Well, to do that, you can do 4 divided by 6, which is 2/3. Oh, goodness. So our scale factor is 2/3. We have to multiply b by 2/3 to get to a. So to get the heights of prism A, we can take 3.75 divided by, times 2/3. Which is 2.5. So this height here is actually 2.5. All right, and now this volume is going to be our 3 lengths multiplied together. It's going to be 4 times 4 times 2.5, which is 40. All right, y'all, now this is the really cool part. I want to take, excuse me, volume. So I'm just going to kind of do this off to the side because this is where we're going to figure out what the shortcut is that we can take. So I'm going to take the volume of our prism A divided by the volume of prism B. All right, so the volume of prism A was 40. Volume of prism B is 135. All right, now we're going to simplify that. Let's see, we can divide them both by 5. So 40 divided by 5 is 8. 135 divided by 5 is 27. And I want you to take a second and think, how does this relate to our scale factor? Remember that our scale factor is over here. We multiply by 2/3. So 2/3 was our scale factor. How does this relate to our scale factor? All right, this is equal to 2/3 cubed. Because remember, when you cube a fraction, you cube the top and you cube the bottom. 2 cubed is 8, 3 cubed is 27. Y'all, the ratio of these volumes is always going to be your scale factor cubed. Always your scale factor cubed. So we didn't need to do all of the work of finding the height and finding the height of the other cube and then calculating the volume. We could have gone straight from 135 to 40. We could have done 135. We could have done this right away, times 2/3 cubed. And that gets you 40. Nice little shortcut. So always figure out what your scale factor is, and then the shortcut is to cube your scale factor, multiply by your volume, and that gets you your new volume. Pretty cool, yeah? All right, last topic. And that topic was tricky, and feel free to ask some extra questions if you have any. Or when you have some. Okay. Composite solid. This means, remember, y'all, that you have some sort of combination of solids, or maybe a solid was taken out of another solid, which is our case. So here we have a cylinder with a triangular prism taken out of it. So this has like a hole in it. We're going to try to find the volume of this composite solid. You might think this is the volume of the cylinder. I'm going to abbreviate that cylinder. That's cool. Minus the volume, I'm going to abbreviate that vol, of the triangular prism. I'm just going to write triangle prism. Abbreviation. So if we find the volume of the cylinder, subtract the volume of the prism, that will be what's left over, all of this stuff, that is what we want. All right, so first steps first, find the volume of the cylinder. Volume of the cylinder, if you can remember, is pi r squared times the height. And the volume of the prism is, actually, nah, let's deal with that next. So we're just gonna leave this here. Volume of the cylinder, let's deal with that first. Pi r squared h. Pi, what's the radius of our cylinder? Ooh, you might see this sneaky down here. The radius of our cylinder is this line right here, which is 10. So this is our radius. So pi times 10 squared times the height. What's the height of our cylinder? 32. That's actually the height of both our cylinder and our triangular prism. All right, so let's see. Pi times 10 squared times 32. This is 3200 pi. I just took 10 squared times 32. So I'm just going to leave it like that. And now I'm keep writing this dash. This is the subtraction sign. So now let's just leave that like that and move over and find the volume of the prism. Volume of this prism. The volume of a prism is base times height. We need to find the area of our base and multiply that by the height of the triangular prism, which is 32. We already know that. That's 32. That's supposed to be an arrow. Now the base is a triangle. So this is going to be 1/2 the base of the triangle, which is 12, times the height of our triangle, which we don't have. We need to find that. The height of the triangle, remember, is like take a triangle, draw a line straight down. It's the altitude. How should we find that? Well, okay. This side is 10. And if we cut that altitude, that means this side of the triangle will be half of 12, which is 6. We can use Pythagorean theorem to find that altitude. Yeah, I'm going to call it A. Okay, so Pythagorean theorem says that a squared plus 6 squared equals 10 squared. All right, so let's do 10 squared minus 6 squared. That's 100 minus 36, which is 64. So that means we end up with a squared equals 64. And then we square root both of these, and we get a is equal to 8. Therefore, our altitude is 8. So that's the height of our triangle base. Whew, all right. So that's the area of the base, this whole thing. So I can I'll highlight this. This B, this base, is this whole thing. Area of that triangle, that top triangle. All right, times the height of the triangular prism, which is 32. All right, y'all, and I'm going to help you out here. 1/2 times 12 times 8 times 32 is 1536. All right, and then 3200 pi minus 1536 is approximately 8,517.10 cubic centimeters. So for composite solids, figure out if you need to add or subtract a solid from another one. So if you've got a hole in a solid, then you'll have to subtract, and then find the area of each solid, and then subtract or add them, depending on the problem of the situation. All right, y'all, that is it for this set of notes. That's it for this, so please email me if you have any questions at all over the video or anything else that you're working on, all right?